continuing on this idea of geometrical representation of our complex numbers and this idea of locus, however you say that word. We saw circles before, so we briefly mentioned it. Here it is, our basic circle, and we said, oh, we could now describe this as z times z conjugate equals r squared. But now we've got another way, because now we know about modulus. Remember, z times z conjugate is basically the modulus squared. So another way we could write the equation of this circle is simply the modulus z is equal to r. Now, if you think about what that actually means, what is the modulus of z? It's the distance of the point to the origin. Well, what is a circle? A circle are all the points that are the same distance from the centre of the circle. Well, that's what it is. So we say every single point on this circle would have the same modulus. It has the same distance to the origin. So the thing to be careful about here is, remember, it's r, not r squared. We're so used to writing equations as a circle equals the radius squared. But in this case, we're actually saying that the radius is the modulus of z. So the length of the vector, if you like. Now, if we were to move that circle to some other centre, let's say it's omega, again, if we think about it, that idea, now we saw it in the conjugate way of writing it before, but now we could simply say, well, the length of every vector that joins every point on that circle to the centre must be r. Doesn't matter where we place it on the circle, the distance from that to the centre will be the same. It's still the same idea from coordinate geometry. When we shift something, we just go, well, minus the shift. So we're saying z minus where we've shifted the centre to. So what are these circles? X squared plus y squared equals 16. Well, I know that's a circle where the centre is 0 and the radius is 4. So I know it's the modulus of z is equal to 4. If I wrote it in conjugate notation, it would be z conjugate is 16. Well, what about this one? Going to need to find the centre, so complete the square. Half the coefficient of x would be 3, and half the coefficient of y would be negative 2. 3 squared's 9, negative 2 squared's 4, so 9 and 4 is 13. Add that to the 12, we get 25. We can now see, the radius is 5, the centre would be at negative 3, 2. So I'm saying it's the modulus of z plus 3 minus 2i is equal to 5. So z minus the centre. In conjugate notation, that would be z plus 3 minus 2i, but then the conjugate of z, and then the conjugate of 3 minus 2i is 3 plus 2i is 25. Alright, let's go the other way. Find the centre and the radius of modulus of z minus 5 minus i is equal to 2. So the centre is 5, 1, because it would be the complex number 5 plus i. And the radius is 2. There's one in conjugate notation. So the centre, you always look at the z, not the z conjugate, to work out the centre. So z minus the centre, so the centre must have been negative 4, negative 1, and the radius in this case would be 7, because in this one it's radius squared, so radius is 7. Oh, hang on. Not immediately obvious. I'm going to have to play around with this one. What can I do? Well, I could pull the 3 out, because we know the absolute value of 3 is 3. That still doesn't really tell me what it is at this stage. What is it saying? It's saying I want all the complex numbers such that the length when I join it up to the origin is 3. Well, 3 times that length would be the length when I join it up to the point negative 2, 1. What the heck's that? So let's get it back to Cartesian form, and maybe I'll then recognise what it is. That's 3 times the modulus of z, that would be 9x squared plus 9y squared. I've squared both sides. And then on the other one I'll get x plus 2 squared plus y minus 1 squared. Expand it out. It's starting to look like a circle now, because I can see the coefficient of x squared and y squared is the same on the left hand side, also the same on the right hand side. So when I pull it all together, I've got 8x squared and 8y squared. Yeah, that's a circle. Coefficient of x squared and y squared is the same. I don't like completing the square on 8x squared, so I'll divide everything by 8. Now I can complete the square. Half the coefficient of x, well, negative half, that becomes negative a quarter, half of that. And then on the y squared one, half of a quarter is an eighth. A quarter squared is 1/16, an eighth squared is 1/64. So I've got to add those to the 5/8. I get 45 on 64. Remember, nothing says it has to be a nice, neat number. But there it is. The centre is a quarter minus 1/8, and the radius would be 3√5 on 8. That would be that particular circle. Z conjugate plus 2 times Z plus Z conjugate. Again, not immediately obvious what I'm talking about here. Let's put it in Cartesian form. Z conjugate, x squared plus y squared. And when we add a number with a conjugate, we get twice the real part, so that's 2x. But this is also multiplied by 2, so we get 4x. Okay, yeah, that is indeed a circle. Let's complete the square on that one. I get x plus 2 squared plus y squared is 4. Centre negative 2, 0. Radius is 2. So if we recognise it straight away, if it's a nice familiar one, simply modulus of z equals something, we know, oh, brilliant, circle. If it's in conjugate form, great. But if I don't recognise it, then I'll draw it back to Cartesian form and then see what the equation is. And maybe I'll recognise it in that format. Okay, the other thing we saw before was lines. We said horizontal lines, they would all be the imaginary part of z is equal to a constant. Vertical line, we said the real part of z would be equal to a constant. But of course not all lines are horizontal or vertical. What happens when we have a line at some angle? Here's a way of thinking about it. It's a perpendicular bisector of 2 points. Now what are the 2 points? Could be any 2 points really when you think about it, such that the distance is the same. So if we see this situation then, it should look something like this. The distance to one complex number is equal to its distance to another complex number. Then that will be a straight line. It'll be the perpendicular bisector of those 2 points. So any line we should be able to write in that sort of format. So we just have to find that perpendicular bisector and then that's the line. So something like this one, I see it, modulus equals modulus. I'm saying distance to 1 plus I is the same as distance to minus 2 minus I. Alright, I know it's a perpendicular bisector. I know it's going to be a line. Well, if I didn't see it that way straight away, I could go, let's get it back into Cartesian form and see if I recognise what it is. Left hand side, I'll get x minus 1 squared plus y minus 1 squared, and on the right hand side we'll get x plus 2 squared plus y plus 1 squared. I'd squared both sides if you like to get rid of the square root signs. Expand that all out, collect like terms, and we get the equation of a line. 6x plus 4y plus 3 is equal to 0. But if I do recognise it as a perpendicular bisector, and the 2 points would be 1, 1 and negative 2, negative 1, there's still a bit of work to do. I'm not going to say this is going to be quicker than the other one, but it is a different way of thinking about it. How do you find a perpendicular bisector? What do I know? I know the line has to go through the midpoint of the 2, because it's a bisector. So I can find that midpoint, negative 1/2, 0, and it's perpendicular to the line that joins those. So if I find the slope of the line joining these 2 points, 2/3, well, it's perpendicular to that. So the slope I want is negative 3 on 2. Put that into my point slope formula, playing around, we get the same equation. There's still a little bit of work to do, but it gives us another way of thinking about things, which when it gets to a question like this, that idea becomes useful, because notice it doesn't say find the equation of this, it simply says sketch it, just draw it. Well, if I think of it as it's the perpendicular bisector, then I know it's the 2 points I've got, conveniently they're purely imaginary, so it's going to go minus 2 and 4. Perpendicular bisector, well, halfway between minus 2 and 4 is 1, and perpendicular to the y-axis would be parallel to the x-axis, and there it is. I could give that equation because it's a quite simple one, but again, they haven't actually asked for the equation, they simply said sketch it. There you go, I'm drawing it. There it is. I've drawn the perpendicular bisector of those 2 points. Alright, so that was circles and lines. Rays. Okay, cast your mind back to year 7 maybe. Remember, there's 3 types of things. There's rays, intervals and lines. And lines are the ones that extend out to infinity in both directions. Intervals are the ones that have a definite starting and finishing point. Or rays are the ones that's in between. Has a starting point but then goes off to infinity. A ray then we can describe using complex numbers, using arguments. So here's a ray centered at the origin. What do all the points on this ray have in common? They all have the same argument. They all are going in the same direction. So I could describe it as simply the argument of z is equal to whatever that angle is. And that would describe that ray. Again, I could move it. It doesn't have to start at the origin. There we go. That would be the argument of any vector joined up to omega is equal to theta. Now you'll notice I've circled the starting point. Because remember, the origin has no argument. You can't find the argument of 0. Because until you start, you don't know what direction you're going in. So whenever we've got a ray, we would circle the starting point. It's not part of the description here. Now we can do regions in the plane, like this. We've got 2 things happening here. First thing, we want every complex number such that its distance to the origin is less than 1. That's the inside of a circle. The circle would be dotted because it's not included. The boundary is not included. Radius would be 1. We know we're inside that circle. But the other thing we know is the argument of these complex numbers is going to go in between 0 and pi on 4. Okay. Well, there's the ray where every complex number there would have an argument of pi on 4. And there's the ray where every complex number has an argument of 0. And we want in between those. So inside the circle, and we're in between these 2 lines, we must be in that little sector there. But a couple of things I have to do. Whenever a boundary is dotted, then the intersection point is excluded. Because it's not included as part of the solution, because we're saying it's this and it's this. Well, that point of intersection is only the second one, it's not in the first one. So I circle those points, and I should have also, now I think about it, dotted the ray outside the circle, because they're not included either. So technically they should be dotted as well. Sketch this one. So I look at it, and I see modulus z. So I want every complex number such that its distance to negative 2, 2 is equal to 2. Well, that's a circle. And it must touch the axes. Because if the centre is at negative 2, 2 and the radius is 2, then it must just simply touch. Those axes are tangents. Now when you get a question like this, don't get lazy and just draw your circle so it overlaps the axis. Because they're going to look at that and think, oh no, that's the wrong circle. Because it just touches, it's just a tangent. So make sure you give a good graph when you do this. Alright, that was the first part. What are all the possible values for an argument of z that lies on that circle? So every point there, what do the arguments lie in between? Tangents drawn from the origin will give us the minimum and the maximum argument. Because every point in there must have an argument that falls in between those 2 lines. So I just have to find the arguments of those 2 tangents, which nicely in this question is horizontal and vertical, so it's an easy one to do. I mean, if the circle was somewhere else, it might be up at an angle and we've got to do some calculations to work out what those arguments are. So I know it's in between pi on 2 and pi. The thing to note about this one, technically I should have used capital A there, not little a. Remember, capital A is for principal arguments. If I was just to say argument with a little a, then theoretically it could have any value because you could keep going around. So there'd be a whole heap of different sections it could be. It could be pi on 2 to pi, but then we could go around again, and what would we get? We would get 3 pi, and what comes before 3 pi? So 5 pi on 2, I think. Yeah. So 5 pi would be a solution. Technically I should have had capital A there. What about if they ask for the minimum and maximum values of the modulus? So all the points on that circle, every complex number, which one's furthest away and how far is it, and which one's the closest and how far is it. This is how you do it. Distance to where? Well, it's distance to the origin in this case. So what we would do is we would draw a line going from the origin to the centre and then extend it through. That will give us the closest point and the one that's furthest away. So whichever point you're finding the distance from, join it up to the centre, and that will give you the minimum and the maximum distance from that point. We now have to calculate those distances. Okay, well, we know the distance to the centre. A bit of Pythagoras, we could see that's 2 root 2. So that's how far it is to the centre. We also know the radius of the circle. So the minimum then would be 2 root 2 minus the length of the radius, and the maximum would be 2 root 2 plus the radius. So there's my answer. Minimum of mod z would be 2 root 2 minus 2, maximum 2 root 2 plus 2. Let's have a look at this one. Quite possibly the hardest region question ever asked. We just simply have to sketch this region. We want every complex number such that the real part of z is greater than or equal to the argument of z. Notice it is saying capital A here. So we want the real part of z that's greater than or equal to the argument z. Just to remind myself, principal argument, we're talking the arguments will go in between minus pi and pi. That's what we're interested in. Okay, any region in the plane, we've got to work out the boundary. What is the boundary? Okay, the real part of z would be x. The argument of z, how would I find that? Well, that would be the inverse tan of y on x. Let's get rid of that inverse tan. We'll tan both sides. So tan x is y on x. Y is x tan x. That was the first thing they had to do, is to work out this boundary. What on earth does that look like? This now goes back to, well, I guess it was Tudor stuff, isn't it? Multiplying two curves together, what does the picture look like? Okay, well, there's the two curves. The red one is y equals tan x. The blue is y equals x. We're going to multiply these two things together. Things I know. X is an odd function. Tan x is an odd function. Odd times odd gives me even. Now I know this x tan x must be an even fraction. It's going to be reflected in the y-axis. That kind of helps me, because I really only need to then draw half of it, because I can reflect it and get the other half. Where does it exist? Well, between 0 and pi on 2, this would be a positive number, so I know I'm in that section there. The vertical asymptote creates a boundary in this, so it might change after that. I said it was an even function, so that would reflect over. That's got to be positive as well. Over in between pi on 2 and pi, well, pi on 2 times pi, that will give me a negative number, right? Because the tan of a number in between pi on 2 and pi is negative. So now I've got a negative times a positive, gives me a negative. That would reflect over. The domain of tan x is minus pi to pi. It would end up looking something like that. Remember, the curve bends towards the asymptote. You got the tan function in here, so it does this funny shape here. Now we've got to work out which region we're in. Let's test some points. I need to pick a point that I know the location of. Let's start in the first quadrant. And I know all the arguments in the first quadrant are in between 0 and pi on 2. I know that. I'm going to need that information, of course, because we're saying the real part's got to be bigger than that. Now, I've picked a point. I've picked pi on 2, 1. Now, I know it's sitting on that asymptote, but remember, inverse tan is what we're dealing with, but the actual inequality, it doesn't involve the tan function, it's simply the argument and the real part. I can still substitute this number into that. Now, I've found a point that I know its location because it's sitting on that asymptote. If I was to sub that in, well, pi on 2 plus I, that's the point. Well, pi on 2 is going to, because remember the real part is pi on 2, has got to be bigger than the argument because pi on 2 would be over here, the argument, well, I don't actually have to work out what that argument is. I can see that it's going to be less than the one we want. So, yep, it's included. All right, I know I'm in that section. Let's have a look over in the second quadrant, what happens there. So by the way, you'll notice that these vertical asymptotes, as I said before, they're not boundaries for this curve. It's the curve that is the boundary. So that's why I haven't used the asymptote as what's happening on the one side of it and the other. Simply the curve I'm looking at here. Okay, second quadrant. Well, that's where arguments will go in between pi on 2 and pi. Well, hang on a sec. All the points would have a negative real value over here. I don't need to go any further because I know the argument's positive there. So when is the real part bigger than the argument? Well, it never will be, because the real part's always going to be negative and the argument's always going to be positive. So no points are included in quadrant 2. Okay? Let's move to quadrant 3. The argument will go in between minus pi and minus pi on 2. Again, let's pick a point. Well, let's make it minus pi on 2 minus 1. The real part of that is minus pi on 2. Minus pi on 2 greater than or equal to the argument of it. Well, let's see where it's sitting. Is minus pi on 2 greater than this argument? So here we are. We're in that section there. It is included. Let's go to quadrant 4. Minus pi on 2 is less than the argument is less than 0. Similar to what happened in quadrant 2. Over here in quadrant 4, every real number is positive. And the argument of everything over there is negative. So yeah, every point is included this time. Okay, we've got a picture. There is the region. But here's some interesting things, because if you thought, oh brilliant, I've got it. No, there's even more happening in this question. Because, some things to note. Argument of 0, remember, is undefined. So you can't substitute it into the original equation. So it's excluded. But this whole interval going from 0 to minus pi is excluded as well. Because there, the argument is defined as pi. Pi does not satisfy this inequation. So therefore, it's excluded. And we don't stop at pi. It keeps going. It was the domain of that tan function that was between minus pi and pi. Not the argument. The argument between minus pi and pi doesn't mean the x values can't be that. Now we were talking about the complex number z. Now, z in between minus pi and pi, no. That's not what we were dealing with. It was the tan function that went in between minus pi and pi. So you actually had to extend this all the way to the right. A very difficult question that was presented with that particular year. Playtime.